Well, hello everyone. We got those nice headsets, so you can put them on, you don't have to, but I have to scream very hard. So if you can understand me without them, that's fine by me. So my name is David. I am a software developer in the Netherlands. Been doing that for around 8 to 10 years now. And well, I'm also an Oracle ace, which means that I really like to talk about Java related stuff. And today I'm going to tell you something about the pitfalls of the new concurrency model of Java with the virtual threads. And how we do that, we start with the current situation. What are the current threads that we currently have? And what is the problem that we are facing with them? And then we will start talking about these virtual threads, how they work, and what they are, and when to use them and when not to. And if there is time left, we're going to cover structured concurrency, which is still a preview feature, but I really love it and I love to talk about it, so that's why it's at the end, if I talk fast enough. So this is how we create a thread inside Java right now. Who has done something like this before? Ah, that's most people. The hardcore developers are definitely on the right. So what we do here is that we create a new thread inside Java. We call the thread constructor and we pass it the task. So what happens is that when we do this, we ask Java, can you create a thread for me? And then the code will start doing things and it will go to the operating system and it's create a real an operating thread that the application can use. And then we go back up and then we are at the line again and then we have a thread or an instance of a thread that we can use to, for example, call start. And then in this case, the task will start running. So every time we do this, every time we call this thread constructor, we are going to the operating system. The operating system is going to allocate 1 or 2 megabytes for each thread. And then it is creating a real thread resource for us to use. And then we have a thread inside Java. And as you can see hinted at the top, we call them now platform threads. The name of the thread didn't change, but we now call them platform threads to be able to tell them apart from virtual threads. So we have the new virtual threads and the current threads, and we refer to them as platform threads because they are managed and scheduled by the operating system. So one way of using threads is to create one thread for each task that we have. So in this example, I have 3 tasks, and for every task that I have, I will create a thread, and I will just discard it when it's done. And this is a very easy way of programming, because for every time I just need a thread, I will create one and just discard it when it's done. It's very easy, very straightforward, and everybody can follow it. But it is kind of a waste of resources, because every time I'm going to create a thread, I will have to go to the operating system and go back up. I have to allocate a megabyte of memory only to discard it after the task is done, which is just really a waste of time and resources. So since Java 5, we are encouraged to use the executor services instead of the thread class directly. And what it gives us is that we now have a pool of threads that we can just submit tasks to. So here I have a little blue box with 3 threads in it, and I can just submit tasks to this pool. And every time a thread is available, it will pick up a task from the queue, and it will start running it, and then it will be put back inside, the thread will be put back inside the pool when the task is done. And this will keep going until the queue of tasks is done. So the great thing about this pooling is that now the threads can be reused, so I don't have to discard them, I don't have to recreate them every time. But there are also some downsides or things you have to look out for when using the executor services, and one of those things is to thread locals. If you have a task that sets a thread local variable and forgets to unset it, then the thread will be placed back inside the pool with still the old thread local variable from the previous task. So what happens is that the new task running on that same thread can now also access this thread local variable from the previous task, which is a big no-no. And also blocking methods. When I have a task that is blocking, then the thread is also blocked. It is just waiting outside the pool. It isn't doing anything else. It's not going to pick up a new task. So it's just waiting there being blocked, which isn't really nice. So how can we improve further upon this? And the next thing is async programming. And async programming, well, in my opinion, is very hard to write. It is even harder to read, especially 2 weeks after you wrote it. And it is hard to debug. because the whole Java ecosystem is built around these stack frames, it's built around threads, and with async that kind of goes out of the window and it makes debugging just very hard and reading the code as well. But it does give you better performance for the resources that you have. So let's see how virtual threads improve on all of this. The virtual threads are just an alternative implementation of the thread class, which means that the old threads aren't going anywhere. We just get a new kind of thread, the virtual thread. And the nice thing about them is that the operating system doesn't know anything about it. They are just a concept that lives aside the GVM, which means that the stack frames, the memory the virtual threads use, is all managed by the application itself and not by the operating system. So when we create a virtual thread, we only have to allocate the memory that it needs at that moment. With the platform threads, we would have to allocate all the memory we might use or don't at the start of the creation of the thread. So with a platform thread, we would have to allocate 1 megabyte at the start, but with virtual threads, we only have to allocate a few bytes at the creation of the virtual thread. But the nice thing about this memory is that it now lives on the heap, which gives us the benefit is that it now is also resizable because the application can access this memory. So when the virtual threads needs more memory, we just allocate more, and when the virtual threads needs less, we just allocate less memory for it. And so it keeps resizing during the lifetime of this virtual thread. And that's why we call these threads to be very cheap, because they don't use a lot of memory at the start, and because of some nice blocking features that I will talk about later. So with virtual threads, because they are that cheap, we now can create a virtual thread for each task that we have, which gives us the nice models that we now can create just a task for each, a thread for each task that we have, which is just really nice. So I said that each thread was very cheap. So let's compare them to the platform threads. So here I have a graph. I created one application, or two, and one of them uses the virtual threads and the other one uses the platform threads. And as you can see, when you're using 1 to 1,000 virtual threads or platform threads, you don't really start seeing a difference. Well, at 1,000 you start using a bit more, but it's still the question, am I going to rewrite my entire application if I only have 1 to 100 threads? Because the memory difference is just very small. And as you can see with virtual threads, you can create really a lot of them, even 100,000, which is just fine. Because with the platform threads, I got a out-of-memory exception. That's why there was no blue bar in the last, for 100,000. So as you can see, if you are just using a very small number of threads, then the platform threads are fine. But if you start using a bigger number of threads, then you will see a really big difference in the memory usage of the virtual threads. So how do we create a virtual thread? Well, that's very straightforward. We have two ways, two very easy, straightforward ways. And that's the start virtual thread on the thread class. It is a static builder method that will create a virtual thread for you and immediately start it with the task that it has been given. So in this case, it has been given the print task. So a thread is created, it's immediately started, and it will run this print task that has been given. Another way would be to use the executor services. So they are a bit of like a drop-in replacement of the executors with the platform threads. And with this new executor, the new virtual thread per task executor, it does what it says on the box. It will create a new virtual thread for each task that is submitted. So in this case, I just submit one task, the print task as well. And it will create a new virtual thread and it will immediately start running. And as you will notice, the executor service is now in a try with resource statement, which means that now the executor service implements the auto-closable interface. So it's now closable. So after this try, my executor service is shut down and everything is cleaned up for me, so I don't have to do it myself. And to exit this try, all my virtual threads have to be done. Either they are finished or they threw an exception. because otherwise I wouldn't be able to exit this try. And with virtual threads, you can just do simple things like this, create 100 million tasks, and submit them. And well, this all does sound very nice and easy. With the threads, we probably have an idea how does this run on a machine, because let's say, for example, my system only has a 4-core CPU, so it can only run 4 physical threads at the same time. And with the previous example, I just created 1 million threads. So how does this connect one to each other? And the magic is the carrier thread. A virtual thread does not run directly, so to speak, on the operating system thread, but it runs on the carrier thread. And a carrier thread is nothing more than just a thread designed to run and execute virtual threads. And if I submit a lot of virtual thread or a lot of tasks to my executor service, it starts to look a little bit like this. I will have a queue of virtual threads that need to run. I have, in this example, 4 carrier threads. And those carrier threads run on a thread that's managed and scheduled by the operating system. So really we got a layer of abstraction in the middle, so that we now can just create virtual threads without the memory limitation or, well, rules of that the carrier threads have. So how can you manage these carrier threads? By default, if I have a 4-core system, I would get 4 carrier threads, but you can play with those numbers. By default, you will get as many carrier threads as there are cores available inside your system. So 8 cores is 8 carrier threads, but with this virtual thread scheduler.parallelism parameter, you can change the amount of carrier threads that you get. So in this example, I changed it to 5. So then I will have 5 carrier threads. You can make it more or less depending on what you prefer. And there is a max pool size. There are situations where there are more carrier threads created than what the parallelism parameter says. So in this case, it will be 5. But there are moments where there is a virtual thread being pinned, as I will cover later, and then more carrier threads can be spawned and they will be cleaned up later. Just know that there is a little bit of stretch in there. So how does a carrier thread know when to switch from one virtual thread to another? And that is done with the mounting and unmounting. A virtual thread will continue running on a carrier thread until it encounters a blocking method. And when it encounters a blocking method, it will be unmounted. So the virtual thread is taken off the carrier thread. So its memory, so the memory living on that carrier thread that belongs to this virtual thread, will be copied from the carrier thread back into the heap. And a new virtual thread will take its place. So the memory belonging to this virtual thread that's in the queue will be copied from the heap into the carrier thread. And this carrier thread will now start running this new virtual thread. And the great thing about this is that now the old virtual thread is just waiting, it's being blocked. And its memory is in the heap, where it can wait safely, it doesn't harm anything. And the carrier thread is now running a new virtual thread that isn't being blocked. So now my very precious resource, my carrier thread, is now always doing some work, which is really nice. And to put this in a larger picture, this would be the full life cycle of your virtual thread. It's being unmounted, it's being mounted. It runs on the carrier thread that's managed by the GVM. And then it runs on a thread that's again managed by the operating system. But not every blocking method is ready yet. With Java 21, the synchronize block, a object.wait, or a call to native code using something like GNI would cause the virtual thread to be pinned, which means that it can't be taken off its carrier thread and it will be stuck. And then you get a hit of performance because then the virtual thread isn't being taken off and a new virtual thread can't take its place. Which means, well, like I said, that it's being pinned to its carrier thread. And in those situations, the application can decide to create more carrier threads temporarily to fix this performance issue. But to see if you are using a method that pins the virtual thread to its carrier thread, you can use these two run option or this run option in the system property, and it will print out the stack trace or just a very short description of where your virtual thread is being pinned at the time. So if I would have a method that blocks my virtual thread, and it pins it as well to the carrier thread, then with these two options, I would get a stack trace or just a very small description of when this is happening, and then you can fix it, well, to increase your performance. And now let's start talking about the pitfalls of the virtual thread. So the thing you want to do is not use them for very long-running calculations. These virtual threads are meant to be blocked and block often and or wait a very long time. That's where they are very good at. If you are just running them for a very long time, never blocking them, then they act like platform threads, but you will get a little bit performance decrease because, well, still the overhead of running a virtual thread. So if you have long-running calculations that never block, it would be better to use a platform thread instead of a virtual thread. And of course, you have to watch out for old libraries that have not been adapted to virtual threads. They may still use these methods that pin the virtual thread to its carrier thread. So one other thing is that virtual threads are not faster than platform threads. The virtual thread still runs on a carrier thread, which basically is a platform thread. So they are not a silver bullet. By switching from one to another, it won't increase the performance of your application instantly. So I would recommend you to measure the difference of performance between the old situation and the new situation if you switch to virtual threads, to see if it even makes a difference for your use case. And the last thing is, don't pool virtual threads. They are very cheap to create. So pooling virtual threads really now is an anti-pattern. With the old platform threads, we would want to pool them because they are very expensive to create. But with the virtual threads, they are that cheap. They are really so cheap that you shouldn't be pooling them and just create them just right on the spot where you need them to. So that gives you a really thread per task model, because then you can create a thread for each task that you have. There are some people around that use a pool to limit the access to a resource, for example a database. They will submit database jobs to a pool, and the pool will pick up the task when it's ready. But with virtual threads, like I said, you don't want to pool them, so it would be better to use something of a lock instead. And it will help you solve some performance issues. So I still have 7 minutes left. So I can do a speed run of structured concurrency, because virtual threads are very nice, but structured concurrency is just a bit better. It helps you manage all the threads that you create. Because with 1 million virtual threads, you will get 1 million lifetimes that you will have to manage. And before I dive deep into structured concurrency, I want to show you, show you first a simple example, and let's explain some concepts. So this is just a very simple method. It's just the method A, and it has two calls, one to method B and method B. And then I will create something of the result of those two methods. And this is just very simple structured code. We know exactly what is happening at each line of the code. When I enter this method, I know method B will run first, then C, and then I will create a result and return it to the caller. It is all very straightforward. So the lifetime of these methods is also very easy to put inside a simple drawing. So I have the full lifetime of A, and inside that lifetime, I have my method B, C, and I will create a result. And if something happens to this, very structured example, for example, method B throws an exception, I know that I can stop at that point in the code. I am not going to call method C, I'm not going to create a result, and I will just rethrow this error to the parent. Let him solve it. And this example gets a little bit more difficult when we add virtual threads into this example, because now I have this full lifetime of method A, and now B and C run concurrently. They run at the same time. So if now B throws an exception, method C is still running. It will still get started. There is a thread inside method C that's still running. Method B threw an exception. And now I will wait to try and create a result that I can never make because method B threw an exception. So the thing is that now the lifetimes of C and method, or the threads inside method C and B, is somehow connected. There is an implicit relationship between those two threads. Because if method B fails, I want method C to fail as well. Because only with both of them I can create the result that I want and that the parent or that the caller can use. And that's where structured concurrency comes in. It binds those lifetimes of the threads together. So here I have a scope, the structured task scope dot shutdown on success. With Java 21 you get two shutdown policies. The shutdown on success is one of those two policies. And the policy states when the virtual threads are shut down. So in the case of the shutdown on success, my scope, my virtual thread scope will shut down when the first thread has finished. So using the scope object, I will fork two new virtual threads. One that will return result 1 and the other will return result 2. And then I will do a scope.join. And at the scope.join I will wait for the policy of my structured task scope to finish. So in this case the join will wait on the first thread to finish and then it will continue. And then using the same scope object I can get the result. Well, this is the shutdown on success. There is also a shutdown on failure, which would behave, create a relationship that if one thread fails, the other one will be stopped as well. So the pitfalls really of the structured concurrency part is really managing the lifetime of threads yourself. Structured concurrency makes it that much easier to say when a virtual thread has to live or be stopped. So with joining exceptions and timeouts, you don't have to create that yourself anymore, but with structured concurrency it all comes out of the box. And you don't have to write tests for it, which is always very nice. So with virtual threads, to get started with Java 21, these are the two methods that you need to know. The start virtual thread, which will create a new virtual thread with the given task, or the new executor service that will create a task or a virtual thread for each task that is submitted to it. And right in time. So thank you guys for being here, and girls. Thank you. And